write this in our notebook?
I don't care.
Oh, yeah.
So you just say, I don't care.
I just don't. I thought we had lines in it.
Yes.
How often do you use this in everyday life?
We're going to be looking at what we're going to call parametric equations. Parametric equations, we have different functions that describe our motion in terms of a parameter, parametric parameter, usually in terms of time. We're going to have independent functions, something that describes your horizontal motion in terms of time, something that describes your vertical motion in terms of time. Perhaps you've seen this before in kinematics in physics, just like this. Philosophical problem on my part, and I know this is going to be recorded. Why am I giving revisions? Why am I giving retakes if we're not taking notes? That one's on you. All right. Going through, as an example, you've seen this in kinematics, where you've got your x equals in terms of your horizontal velocity, something for your vertical velocity. Same thing, but why does it have to be a parabola? And typically in physics you have things that are parabolic because that's the way gravity works. It's not only that. We're going to have some equation that describes our horizontal motion. We're going to have some equation that describes our vertical motion. Now, I'm going to use x of t equals y of t equals. I'm going to be consistent with t being our parameter. Now, usually it means time, and so how things are changing horizontally with regards to time, how things are changing vertically with regards to time, and we'll have time is defined in some way. So I'm going to use this notation. I'm going to write that a little bit better. T. I'm going to use this E-looking thing, means is an element of, I might have some bounds. I'm going to write some things like that. This means that T starts at A and ends at B. This means exactly the same as T is an element of the set of numbers A to B. This means the exact same thing as A is less than or equal to T, less than or equal to B. What this gives us is a set of coordinates where our x coordinate is determined at the certain time where we're located horizontally, and our y coordinate portion is determined where we are at a specific time in regards to y. We're going to start looking at this kind of graphically, looking at some examples where we've got the horizontal component, the vertical component. Direction matters. Your position, time, where you are at a specific time matters. So I gave out this practice, and I gotta adjust my lighting so that we can see, we're gonna see how this looks along the way. And there we go. So we're gonna graph some things where, look at it. Up top for each one, I've got a set of parametric equations. So x of t equals 3. So my horizontal component is 3 every single time. My vertical component, y of t, is -2 plus t. Now, we've got two functions. One function that defines the horizontal, one function that defines vertical. And here I'm saying that t is going to range from -4 to 5. So like we start at t equals -4, we're going to end at t equals 5. We're going to have a graph that has a start and a stop. That's how we can interpret this. So in physics, you've had your x equals your v naught plus v t, or your position, or you've got your s or your acceleration, whatever you've had in physics. Looks good so far. We're going to go through and sketch some graphs. Comments, questions, concerns initially. Let's do this. Now, setting up until we get the hang of things, back to graphing, usually we start off with a table of values. So setting up a table, we've got our t, we've got x is going to be defined in terms of t, we're going to have y is defined in terms of t. So starting off like -4 to 5, if t is -4, we can find the value of x at time equals -4. We can find the value of y at time equals -4. That t goes into the function. So x of -4, well, x is always 3. Y, it's going to be -2 plus t. If t is -4, we've got -2 plus -4 gets us -6. This value, it's saying at time equals -4, the x value of our coordinate is 3, the y value is -6. That gets us a coordinate. So 1, 2, 3, -1, -2, -3, -4, -5, -6. So at t equals -4, we've got this point right there. That's what that's saying. John?
Are these graphs continuous?
Sometimes. For us, yes. Right now, yeah. We're going to go from starting at -4, ending at 5. So it's going to be smooth. Every point's in between. For the most part, our graphs are going to be continuous and connected. Yeah. Oh, there's one point on our graph. That's actually going to be the starting point. We can find additional points. If t equals -3, we could plug it in for the x equals. We can plug it in for the y equals. If t is -3, then x is still 3. Big surprise. If t is -3, then y is -2 minus 3, -5. Okay. So -1, -5. There's t equals -3. We've got another point on our graph. Now, I'm picking some points that are easy to substitute in. We could do -3.9, -3.8, -3.7. Those points are connected. So as we go along, we're going to be connecting our points. Like we were here. This describes motion. We were here at t equals -4. Now we're moving. Okay, moved up. Oh, maybe we can start to infer x is always 3, y. I'm reading this. Y starts at some point and it's moving. Oh, there's a slope there at a rate of 1 y unit per t, per time. -2. If we try that, just plotting points, well, x is still going to be so +3, y, -4. Ooh. What's happening to our motion? Where are we going?
Up.
It's just going up. Well, we're going up until time equals 5. So I can infer everything in between. T equals 5, this is our end. So x is still 3, y is now -2 plus 5 gets us +3. -3, 1, 2, 3. That's where we're at t equals 5. And move straight up. We have a start, t equals -4. We have an end, t equals 5. We have moved up. Just like with vectors, now a vector, there was no change. It was always the same. We have a direction. I'm going to put an arrow on my graph to indicate the direction. I don't need to label every single point there because we're going to have 9 points going along. It takes a bit of time, but I've got a start, I've got an end, and I have a direction. There's a parametric equation, or a set of parametric equations gives us a graph. For our parameter t, time, it gives us something for the horizontal, it gives us something vertical. And when we combine those are each a pair of coordinates. Yeah.
Do you have to do the arrow? Can you do all the dots?
If you label them so that it shows where we're starting, where we're going, what our motion is. If I have a picture of you at the end of the hallway over by B, and then a picture of you over by the end of the hallway down towards the field out back, which one came first and which one came second? Put an arrow in. Put an arrow, that gives us direction. Playing the game, quiz, test, exam, put an arrow on. I will count a point for the arrow. Just like with vectors, we needed direction. I want to see where we're going. Let's get something a little bit more involved. Now that one, the x was constant. Notice that turned into a vertical line. Not a function in our traditional sense. Each input matches with exactly one output. A vertical line is not a function when we have y equals x. But it's a function using parametric equations. And parametric equations, when we've got something that defines x, something that defines y, it opens up a whole new world for us where things that were not functions before can be defined in terms of a function for the horizontal, a function for the vertical. All right, let's do the next one. T, our time, our parameter is going to go from 0 to 3. I've got my table of values set up. We're going to go from 0, 1, 2, 3. We've got to start, we've got to stop. I can figure out what's happening horizontally, what's happening vertically. So I take T, plug it into each function. Horizontally, if T is 0, then x would be -2 times 0 plus 3 is going to be 3. If T is 0, then y is going to be 3 times 0 minus 8, -8. 3, -8. That gets us a coordinate. So it's an xy pairing. It's a coordinate 3, -8. So 1, 2, 3, -8. I like to put down just a note. That's where we're starting. I'll put down like t equals 0, so I have my initial point. Motion matters. Any guess what this graph is going to look like off of our limited experience?
Like a slope.
Like a slope. What's the slope of our line going to be?
Positive.
Okay.
Negative.
Okay. Well, let's pick another point. T, you want to just jump right to the end point? T equals 3?
Yeah.
Okay, T equals 3. If we plug in T equals 3, we've got -2 times 3 is -6. -6 plus 3 is -3. If T is 3, we've got 3 times 3, 9, minus 8 is 1. -3, 1. That xy gives us a coordinate. So -1, 2, 3, 1. There's T equals 3. That's going to be the end of our path. Is it just a straight line? Yeah? Did you plug other points?
It is.
Okay. Look at this. X is linear. Y is linear. Well, if we've got x is moving at a linear rate, thinking like y equals mx plus b, except now it's x equals mt plus b. X is moving at a constant rate, -2 for each time that passes. Y is moving at a rate of 3 per time that passes. So that's really our slope there. T equals 1, just to see it, if t equals 1, we've got -2 plus 3 gets us 1. That'll be 3 minus 8 gets us -5. So 1, 1, 2, 3, 4, 5. There's t equals 1, right on that line. Well, x moved back 2, y moved up 3. And so we've got that. Our direction, I'm putting in an arrow. I've got a direction. We're going to see, we can find slope if we're talking y equals mx plus b, but we've also got a start and a stop based on that parameter, based on time we're measuring from 0 to 3. That's the general idea, parametric equations. We've got one function that gives us the horizontal motion, one function that gives us the vertical motion, and combined, it gives us a coordinate that shows us a path over time. There. All right.
So if you erase all those dots and just have the arrow with no dots.
I need a start, I need a stop.
If you just have the arrow,
That's fine.
like not even the start and the stop dots.
Give me the start and the stop. I'm going to change things up over, no pun intended, time. how would it be different if I put in 0 to 3? Oops, my notation. I'm gonna use this E. This E thing means is an element of, or T goes from 0 to 3 versus T. Think back to our past use of notation.
Well, it stops. It's just like a line segment with the square ones.
0 and 3 would be.
Line segment, yeah, with 0 to 3 with the square ones. What about if I use the parenthetical brackets?
It
Until
continuously
almost.
goes.
It continuously go, starting at 0,
Yeah.
ending at 3.
But it doesn't actually start at 0.
It doesn't actually start. It starts immediately after 0. What I would do for this is we do not include the endpoints. If we had something like that, we would not include the endpoints. So it's exclusive. This is like 0 is less than T is less than 3. Does not include the endpoints. So we would use an open sort. Put the points to give us an endpoint. Or when I throw that at you, think about that. All right, let's do another one. Third one. Take a guess at what that graph will look like. X is T minus 3. Okay, that's linear. So X is moving like left to right. Y is T squared minus T. So Y is parabolic, quadratic. All right. Number 4 is one of my favorites. Actually, number 6 is, I like number 6 better. All right, number 3, we've got T, we've got X, we've got Y, plugging in some points. T is -2, we're gonna go up until 8. T is -2, the -2 minus 3 gets us -5. And Y would be -2 squared is 4. 4, -4, -2, that gets us +8, so that's 4 plus 8 is 12. -5, 12. -5, 12 is, oops, that's off the graph. That's somewhere up there. -1. If T is -1, that's going to be -1 minus 3 is -4. Okay, the X is moving normally, linear, just adding 1. We can see the slope. -1 squared is 1 plus 4 gets us 5. So -4, 1, 2, 3, 4, 1, 2, 3, 4, 5. So our Y is, from there to there, 0. That's going to give us -3 and 0. 1, 2, 3. Let's move from there to there. 1. That's going to be -2. And then 1 minus 4 is -3. 1, 2, 3. Kind of getting the idea. It's -1. That's going to be 4 minus 8. -4. 3, or that 8. That's going to be 0. 9 minus 12 is -3. Uh-oh. We're going back up now. Oh, it's a parabola. It's a quadratic. 4. Maybe we can guess. That went -3, -4, -3 is going back up. That's going to be 1. That's going to be 0. By taking the bits along the way, we can see, we can map out what it's going to look like. We see that we've got that symmetry there. And then we're off the graph again. Thinking, why does that make sense? Well, our X was moving left to right. So I'll put my arrows. Our X was moving left to right based upon T minus 3. Well, X is increasing a rate of 1 per time. Like the slope of X was 1. Well, the y is quadratic, so if x is moving horizontally, well, the y is quadratic. It's going to decrease, increase. Yeah. Now let's have some fun. Comments, questions, concerns. Yeah.
So we don't put arrows at the endpoints in this case?
Because we're going -2 to 8, it stops.
Okay.
There's a set start, there's a set stop. Thinking back to like algebra 2, graphing, everything, like you would have your parabola and it would go up to infinity. It would keep going. This does not keep going. We could just say that t is all real numbers, then it would keep on going in both directions. But because we have an end, a beginning and an end, it stops. We do not have arrows on the end of our graph. It stops there.
Mr. Langston?
Yes.
For that one, what if I don't want to go from -2 to 8, but I want to know, like, because I know that it's a parabola,
Mhm.
but I don't know how far to go down and up.
You mean like what's your vertex?
Yeah. Do I, like, is there like a way that I don't have to go through -2 to 8?
To find your yes. Yeah, same way you would find a vertex before. Here's what I look at. We've got that, good question, that the y, since we want the point where it turns around, that's going to be the axis of symmetry for the y. The y is going to change direction. So the y is t squared minus 4t. Looking at this, we're going to have y is equal, I can factor out a t, that's t minus 4. Let's compare, if we factor that, well, y is 0 at t equals 0 and t equals 4. Does this, and so our axis of symmetry is going to happen when t is halfway between our zeros at t equals 2. So if we look at that, at t equals 2, that was the lowest point that we have. So we'd have to find the time when it's halfway between the zeros for the y. All right, time to get funky. Let me some paper. All right, we're going 5 cosine t. Five cosine t from 0 to 2 pi. All right, interval. I'm not going to go, well, I can do 0. 0 is nice and easy. But after that, I'm not going to go 1, 2, 3, 4, 5, 6, because I don't know the cosine of 1 or the cosine of 2. I know some cosines, some nice values in there. Pi over 2s. Once we go by by pi over 2s from 0 to 2 pi. Is that enough to give us a graph?
Yes.
Okay, let's try it. 5 cosine of t. If t is 0, what's the cosine of 0?
0.
1.
1.
Remember back in September when I said trig lasts all year. Trig lasts until next year. Cosine of 0 is 1, but then times 5, so it's actually 5. 2 times 0 is 0. Sine of 0.
Well, 0.
1, 2, 3, 4, 5, 0. We got a point there.
Wait, because then
And actually 2 pi is going to be the same thing. 5, 0. So there's t equals 0. There's also t equals 2 pi. It's going to be at the same point.
circle.
Ooh. Is this a circle? Well, how do we define the x in a circle? Think about a unit circle. X is cosine. How do we define y in a circle? Oh! It's almost a circle.
Almost?
Well, look, it's at 5. All right, pi over 2. Pi over 2. Let's test. Pi over 2, cosine of pi over 2 is 0. So that's going to be 0. Sine of 2 times pi over 2 is going to be pi. Sine of pi is 0.
I'm sorry. Is it a square?
Is it a triangle?
Pi. Negative 1.
Negative 1.
That's going to be negative 5. Sine of 2 pi is still 0. 1, 2, 3, 4, 5. We're at negative 5. 3 pi over 2.
Are we going down the line?
We started here. There's t equals pi over 2. There's t equals pi. Well, that's 0 again. And 2 times 3 pi over 2 is 3 pi. Sine of 3 pi is 0 again. So it started here. Then it went here to the middle. Then it went to the left. Then it's back here.
So a semicircle.
Oh,
It's a flat circle. You're looking at
What part of that looks like a circle?
Parker's got an idea. Did you put it in the calculator or anything? No. Look at the difference here. Sine of 2t. 2t. What's the period?
Period.
What's the period of sine of 2t?
I don't.
Pi over 2.
You know what
It's actually pi. Let's put in some more points. Pi over 4. Cosine pi over 4 is 0.7. Cosine of pi over 4 is root 2 over 2. Root 2 over 2 is about 0.7. 0.7 times 5. 0.7 times 5 is 3.5.
How do you know it's
I'm telling you. Or plug it in the calculator. So cosine pi over 4. I'm in 0.7. Oh, you can't see that. If we plug it in, that gives us 3.
it's on that line?
1, 2, 3.5. 1, 2, 3.
Oh, what?
Oh, there's t equals pi over 4.
But
0 to pi over 4 to... Now this is rather difficult to start C.
why'd you connect those two? How does that what you're supposed to do?
I'm going to go into the calculator.
Yes.
Also, every time it changes direction, you have to do an arrow.
Yeah. We can graph these in the calculator. Here's what we're going to do. Calculators need to be turned on. We're going to have one equation that gives us our horizontal motion, one equation that gives us our vertical motion. If we go into y equals, well, that's just y equals in terms of x. We don't want that.
No, we don't.
Go to mode,
Where's code?
where you change from radians to degrees. Number 1, make certain we are in radian mode.
Oh.
Underneath that, you see func, par, pole, sec. Par stands for parametric. Pole stands for polar, sec stands for seq. Select parametric. And now go back to y equals. Oh, it's different. We are graphing in a different mode. We are graphing in parametric mode. We have one equation that gives us our t. Now, it was 5 cosine t. Notice when you hit the x button now, it gives you a t instead. You ever look at the x button and wonder why there's an x, t, theta, n there? Those are different modes. You are graphing in different modes. So,
Because I was trying to spell words for that. I would click alpha.
I've got 5 cosine t. Well, the other one was what? 3 sine 2t.
Stop mode. XT.
polar mode, which is really cool.
Calculus?
Nope.
Free calc?
Yup.
Oh yeah.
It's coming up. That was polar mode was what got me into math. All right, window. I'm going to window.
Oh my god, it is 7.
My window, 0 to 2 pi. My t-step is good. I'm going to graph.
Wait, can you go back?
What's a good T-step?
Wait, what's a T-step?
It's an infinity.
Keep it what it says.
That's not what I got.
Wait, no, I don't want it.
All right, put yourself in radian mode. Turn off the stat plot. Zoom 6. We get what's called a lemniscate. Ooh.